All right, so kind of looking at the difference that we've had in the prior example. In the prior example, for the first portion of time, only entries came in. And then for the second portion of time, only entries went out of the box. And so now what we want to do is we want to sometimes take a look at this idea that it's not always two independent events, that sometimes you gain and lose at the same time. Like the example that they have here is this idea of pouring water into a bucket that has a small hole in the bottom. So you're pouring in at a certain rate, but yet it's coming out the bottom through the hole in a second rate. So there's a rate in and a rate out. So when you calculate your net change when you are doing this, you have to remember that it's a combination of what's coming in and what's going out. So you want to have like I guess you want to say your total rate would be the rate in minus the rate out. So that way you have the combination of the two rates. So what you have at any given moment is going to be a combination of what you started with plus what you've accumulated minus how much you have lost. So if we think of that going back to our FTOC and how we were using that to calculate, how much I have at the end is going to equal how much I had at the beginning plus the amount that I gained from A to B. So we might call this, we'll do rate 1, rate in of x dx. So there's some rate function that describes what comes in minus how much you're actually losing, your rate out function, whatever that is, dx. So it's a combination of these two things. So it's how much came in minus how much went out, plus what you started with. You always have to remember you got to include what you started with, all right? So let's take a look at example 6. And again, we're going back to this idea where I'm giving you a graph. I will take a look at the graph and we'll see how that is coming into play in this one. So let's read through the problem together and then you're going to try it. All right, so we have 700 people in line for this ride when the ride begins. I'm going to highlight that because that's an initial value. So they're telling me how many I have to start with. Once the ride begins operation, it's going to accept passengers until the park closes 8 hours later. So there's an interval of time, 0 to 8 hours. When there is a line, people are going to move on to the ride at a rate of 800 people per hour. And notice that the people getting on the ride is equal to the people who are leaving the line. So this is a rate of people leaving the line. The graph that's given is showing the rate that the people arrive at the line. So you have a rate in and you have a rate out from the line. So this right here, it's actually a constant. So this is my rate out. And then this R of T, and when people arrive to the line, is going to be my rate in. And you do want to look for problems on the AP where they have this combination going on. Time is measured in hours since the time the ride begins. So let's see what they're asking us. How many people arrive at the ride between 0 and 3? Again, how many people I have at 3 is going to equal how many people I had at 0 plus my net change, plus my net change. And make sure that you recognize that there are people coming in and there are people leaving, so be careful about that. All right, is the number, notice in this one, this isn't the amount of people. Let me back that up. I just said something wrong. This is the people who arrive at the ride. So I'm not asking about who's in the line. The combination of leaving and going is what's in the line. These are only the people that arrive at the line. So make sure you're only using R of T for this one. B, is the number of people waiting in line to get on the ride increasing or decreasing between 2 or 3? So you have to think about defining a function. Let's say W of T is the people waiting in line. And then you can think about that W of T, the number of people on the ride, is going to increase when its derivative W prime of T is positive, or when its derivative W prime of T is negative. And remember, the total rate, your net rate in IDEA, is going to be a combination of the rate in minus the rate out. So you want to think about that when you set this up, that you actually don't need to find WT. You simply need to have a definition for the derivative of WT, and that is going to be a combination of the rate in minus the rate out. So the rate that they are waiting in the line is the rate in minus the rate out. Okay, I'll leave that for you to think about. And then we have at what time t is the line for the ride the longest. So W of t is going to be how many we have waiting, and we want to know when WT has a global max. Now, just to kind of change it up a little bit here, you certainly could still do EVT on this. But what I want you to try, let's do a modified first on this one, just to practice a little different type of test that we can run for this. And then also remember that they're asking two questions. At what time is the ride the longest? How many people are in ride at the line at that time? You might want to do it with a modified first, and you may also want to balance it out. Think about what it would have looked like if we did an EVT. Okay, and then in D, now notice in this one, they want you to write, but not solve, write an equation involving an integral where the solution is going to give the earliest time at which there is no longer a line. So that is where we're trying to figure out where W of t is equal to 0. So basically what you have to come up with is an equation for W of t and set it equal to 0. All right, I'm going to pause it. I'm going to let you guys think about these things, give it a try, and then come back to the video and I'll explain the solutions. Okay, so notice that one of the things that when you're creating and discussing this, you may have to define a function for yourself for the problem. So I have people arriving at the ride, and so I named it A of t. You could have decided, since R of t was the rate, you could have done it as R of t. Whatever you do, just be consistent and define it so that they know what you're talking about. And so like this would be the change if you decided to use capital R, kind of like when we have little f, capital F when you're doing this. So define your function and then show your definite interval. Where I am is where I was plus my net change. And then we went ahead and calculate it. Make sure you show your units. For B, the amount of people waiting in line, again, I defined a function. I called it WT. I'm really interested in the derivative of that. Notice I don't have to, in this problem, actually find WT because we know W increases when the derivative is positive and decreases when the derivative is negative. So I really just needed to look at the derivative. And the derivative, the rate that you're waiting in line, is the rate of the people arriving minus the rate that they are leaving. And so what I did is I'm using the graph, and you're basically subtracting a constant from the rate that you have. This right here would be W prime of t. Coming here, I just subtracted 800. Clearly, looking at the graph, that W prime of t, when you subtract 800 from your rate, is going to be positive. And so in my justification, I just said for the interval 2 to 3, W prime of t is positive, so W of t is the amount of people waiting. Is increasing at that point. Now, there are two options for doing the global max on W of t for 0 to 8. Now, I'm going to tell you, I didn't really like the EVT option for this, and I'll show you why when I wrote it up. The beginning part's the same. I need W of t to be continuous. So the derivative, which was equal to this, is continuous because R of t is continuous by looking at the graph. 800 is a constant. W prime of t is then integrable, which means W of t is differentiable, and therefore W of t is continuous. Probably should have said W of t there. I found my critical values. When the W prime of t equals 0 is when the rate minus 800 is 0, when the rate is 800, which from the graph was at 3. We could put our values in here. 0 are endpoints. We had 700 to start with. This one, remember that your waiting in line is how many arrived minus how many left. So I have to do the rate in and the rate out net changes. That changes on my 700, the 3,200 from above, and then I calculated 2,400 because when you do this definite integral, remember it's 800 times 3 minus 0, or 3 times 800. Added those up. And then I needed to do the net coming in. So I have 700 plus the net coming in minus the net going out. And then I had to do a lot of work for this. I had to come back up here and notice in order to do that last one, I had to calculate this area I already had, did this area, did this area, did that area, did that area. So I had to do 1, 2, 3 trapezoids, a rectangle, and a triangle and calculate those areas. And I added those up, and that came up with a total net area of 5,000. And then I subtracted 6,400. Now, we do have to know this was less than 0 when you did this, but so basically what you know is that the amount that are in line at this point is actually going to be 0 because technically once everyone's out of the line, you don't have negative people in the line. So this truly was actually equal to 0 for that time. And then so the max waiting in line occurs at t equals 3 hours by EVT, and there were 1,500 in line. I didn't like this because there was a lot of calculations for that, and it was a little weird at the end. You could have done this by the modified first derivative, and I just thought I would show that. You still want to talk about that WT is continuous, same reasons as above. You still find your critical value, which is t equal to 3, and then you just simply go, hey, well, that has to be a global max at t equal to 3 because the derivative was positive for everything from 0 to 3 and negative for everything from 3 to 8. So I know the endpoints can't be the max because I was at a smaller value went up and then I went down only. So there was no going up and down on that. So using the modified derivative, first derivative test, I can say that that's a global max at 3 also. And there's a lot less work because you didn't have to actually calculate the total area under that curve going out. You still had to calculate W of 3 because they asked for it, and where I am is where I was, plus who arrived minus who left. And then we calculate that just like we did above. All right. For D, you had to calculate your write but do not solve an equation. So make sure that you actually had an equation. One of the things that they lost points on for this is you forgot to put the equals 0. So you basically want an equation for when the people waiting in line is 0, so W of t, which is they were making you write the actual integral equation for W of t, which is where I was, plus where how many people left, plus or subtract how many people arrived minus how many people left. Notice that I did change this right here. Oh, whoops, that was awful big. Let me undo that. That's an X. I started to write an X there, and then I remembered this is W of t. So this variable is t. I changed this one to X, and then t, and then made that sure that was an X. So your integral can be written like this. Some other acceptable answers for this is sometimes you can put 700 in for what you started with and 0 to t, and you can actually combine these two together and just make it r of x minus 800 because this is technically your w prime of x inside of here. So, and that's just showing you how to do that net change as a function so that you can write it as an integral equation. And they didn't ask you to solve it. Sometimes they might, but they did not ask you to solve that in this case. So this would be your integral equation.